Good morning, good afternoon, and good evening, everyone. It's my pleasure to introduce the speaker of today's UK Quantum Fluids Network webinar. It's Makoto Tsubota from Osaka Metropolitan University. And so whenever you're ready, please start your talk, Makoto.
Okay, so thank you very much for giving me a chance to give you this talk in the webinar. And I'd like to thank all participants for attending this webinar. I'm Makoto Tsubota from Osaka Metropolitan University. Today I'm talking about the topics of counterflow turbulence. And my talk is divided into three parts. The first is a brief research history of counterflow. The second, I'll discuss some new perspectives, especially focusing on the two kinds of formulation, the mutual friction and what makes normal fluid turbulence. The third part is my main theme. I'll discuss how is a superfluid turbulence enhanced by normal fluid turbulence in counterflow. So this is a typical numerical simulation which appeared in later. So, quantum turbulence has been long studied in thermal counterflow on superfluid helium-4. In two fluid models, the injected heat flux drives normal fluid and superfluid in opposite directions, and here appears a vortex tangle like this. So in our original two-fluid model state that the superfluid and the normal fluid moves independently. So the normal fluid is supposed to obey the Navier-Stokes equations, and the superfluid is supposed to obey the Euler equations. And these two fluids are driven oppositely by the heat flux W. And if both fluids are stationary and laminar, we know the temperature, both temperature and the pressure gradient is proportional to heat flux W. However, this is a typical experiments for the thermal counterflow. And so when heat flux is relatively small, certainly the observation shows the temperature, both temperature and the pressure gradient is shown to show the such kind of linear behavior by showing by the point dotted lines. However, W is increased, the observation deviates from the linear relations. So additional temperature gradient delta P appears because of the mutual friction. And the experimentalists observed a two-stage transition, T1 and T2. So in order to understand this phenomenon, mutual friction is introduced like this. So because of that, two fluids becomes coupled. And this mutual friction gives the additional temperature gradient like this. And the comparison with the experiments yields the mutual friction is proportional to the cubed of the relative velocity. And the pioneering experiments of the simultaneous measurements of delta T and the second standard attenuation was performed by Joe Byrnes long time ago. And when W is small and the flow is laminar, the second sounded passed through. Nothing happens. However, W is increased and the additional delta T appears. Second sound is attenuated due to the vortex tangle here appears. And Weinen observed the time dependence of the mutual friction due to the vortex tangle like this. Then, in order to understand this time dependence, Weinen proposed what we call now the Weinen's equations, describing the time development of the vortex length density L. So the first term refers to the growth, and the second term refers to the decay. And the steady state dl dt equals 0 is given by the competition between two terms like this. So the square root of L should be gamma 0 times VNS. VNS, of course, the relative velocity, and the gamma zero is important coefficient. And this is called sometimes a variance relation, which is used as a benchmark for numerical simulation or typical experimental works. So since the 1970s, experimentalists observed the two different states of turbulence. And the transition to turbulence was observed to depend on the shape of the cross-section of the channels. In a small aspect ratio channels, such as circular or squared, the experimentalists observed two states of turbulence, namely T1 and T2. In the case of large aspect ratio channels, like rectangular channels, the only one state, turbulence, T3 was allowed. So this turbulence transition is still a great mystery. We don't know why such kind of transition depends on the aspect ratio channels. And several years ago, long time ago, Melot and Barenghi performed a nice linear stability analysis of the positive normal flow. And they found normal fluid may be unstable at the turbulent in T2 state. So this is current understanding. In the small aspect ratio channels, in T1 state, only the superfluid component becomes turbulent, but the normal fluid remains still laminar. In T2 state, both fluids may be turbulent. And also, this is also the case in T3 state. So this is a very recent observation of the coefficient gamma by the Tarhase-Weygos groups. And the upper figure confirms the variance relation, namely square root of L versus relative velocity U. This is the data in the T2 state. And this slope gives the gamma, values of gamma as a function of the temperature. And the lower figure shows the collective data for various groups. And the lower data set corresponds to the T1 state. The upper data corresponds to the T2 state. For example, yes, these triangle corresponds to this is an old experiments by the Martin Tufts. And this is the data in the 1.5 Kelvin corresponds to data. So here is a T1 state, and this is a T2 state. So the thoracic groups collected these data from these works, something like that. So numerical simulation of the vortex filament model plays a very important role in understanding the physics of counterflow. And this numerical simulation shows how the initial 6 remanent vortex rings developed to a vortex tangle under the thermal counterflow like this. But please note, this is a one-way calculation. I'll explain the details soon. And the normal fluid, uniform normal fluid flow is prescribed. And we use the periodic boundary conditions for all three directions. So over the recent past 15 years, our field has undergone the paradigm shift because of two main advances. One is the direct visualization of quantized processes and the normal fluid velocity. The other is high fidelity numerical simulations of fully coupled two-fluid dynamics. There are many important visualization experiments, but here I'd like to refer to only one problem, which is directly concerned. And this is a nice visualization experiments by the Weygos-Tarhase groups. These groups succeed in visualizing the normal fluid profile by using the excited helium molecules. So probably you must be very familiar with these experiments. I don't explain the detail, but the point is the heat flux is increased. The profile of the normal fluid changed from the laminar and what we call tail flattened flow and changing to the turbulence like this. Such kind of deformation of the normal fluid profile should be caused by the vortex tangle through mutual friction. So in order to understand this phenomena, the one-way simulation is not enough. We have to take account of the back reaction from the superfluid to the normal fluid. So this is a sketch of the simulation method we need. Almost all previous simulations were performed by one way. Namely, typically the superfluid is described by the vortex filament model, and we take account of the mutual friction from the normal fluid to superfluid. But we neglect the kickback from the superfluid to normal fluid. So the normal fluid profile was prescribed. But present simulation we need is a two-way simulation like this. So I'll briefly explain the formulation of the coupled dynamics of the two fluid models. The superfluid component is typically described by the vortex filament model by using the Biot-Savart law and the mutual friction like this. Numerically, vortex filament is described by a string of points like this. And normal fluid component is described by the Navier-Stokes equations. And the point is how to couple two fluids properly, consistently. The challenge is something like that. So the vortex filament model is basically Lagrangian, while the Navier-Stokes equations is solved in the Eulerian formulation. So the numerical grids for solving the Navier-Stokes equations do not necessarily agree with the discrete points of the vortex filament. Then what to do? So this is not so trivial. But we know the mutual friction along per unit length. So we count the vortex length in such kind of sub-volume and obtained coarse-graining mutual friction. And we use the such coarse-grained mutual friction into the Navier-Stokes equation, something like that. So I will show the typical result of the two-fluid coupled dynamics. So this is a propagation of the quantized vortex rings and the accompanying normal fluid vortices. These blue lines show the quantized vortex rings, which propagate and shrinking, and accompany the normal fluid vortices. And this is exactly the same as the previous pioneering numerical simulations by Demos Kivotidis and the Carol Barings group 26 years ago. Or this is reconnections of two quantized vortices. When two quantized vortices reconnect, they accompany such kind of vortice around this. So this is a numerical simulation of the thermal counterflow and in the periodic boundary conditions. The white line shows the quantized vortex rings, and the blue and red regions show the positive or negative fluctuation regions of the normal fluid flow. But please remember, certainly the normal fluid is fluctuating. This is still laminar. We consider this is a T1 state, not T2 state. So I'd like to discuss some new perspectives of these topics. So we know the two kinds of formulation of the mutual friction now. So traditional approach and the self-consistent approach. The general formulation of equation motion of quantized vortice in superfluid helium flow is something like that. This is equations motion per unit length. M effective refers to the effective mass per unit length, and Fm refers to the Magnus force per unit length. And there is two kinds of approach for the drag force Fd. In the traditional approach, the Fd is represented by something like that. And these questions come from the experimental values of rotating superfluid helium 4 going back to the pioneering experience by Holvainen long time ago. And if we neglect the effective mass, then we can obtain such kind of equation of motion of the vortex filament. And here, the alpha coefficients the alpha prime is described by the gamma 0 and gamma 0 prime like this. and their temperature dependence of something like that. And most of the previous numerical simulation used this mutual friction. But recently, Luca Garanti's groups proposed another important approach for the formulation. Then, the quantized vortex is approximated as a cylinder with radius A0 and the length delta, where A0 should be much smaller than delta. By using the low-Reynolds number flow around the cylinders, the drag force is written something like that. And the question to D is given like this, by using the Reynolds number flow. And in this case, Jodorowsky force should be included. Probably you know that there's extensive discussions, arguments about the Jodorowsky force in our field. And this is very just complicated, but you can refer to the very nice review articles by Yuri Sergeyev about these topics. And why does the self-consistent approach need a Jodorowsky force? So traditional approach is something, the drag force is something like that. And we assume Vn is 0 for simplicity, and here is a vortex line, and S prime along the tangential direction. And if we ds dt is along this direction, so this first term corresponds to this one. And if the S prime is almost perpendicular to ds dt, this comes like this. So what I want to say is, this drag force is completely opposite to the vortex velocity ds dt. And this term makes the component perpendicular to both S prime and ds dt. But in the self-consistent approach gives this drag force, and this force gives just the drag. So generate the vertical forces like gamma 0 prime. Gamma 0 prime, we need a Jodorowsky force. But anyway, including Jodorowsky force in the self-consistent approach, we can obtain this kind of equations and the coefficients like this. The good news and the advantage of this formulation is it has no phenomenological or experimental parameters. This is very good news. So here I will briefly compare these two approaches. So this is a traditional approach. This is a self-consistent approach. The equations of motion are almost similar, but the amplitude of mutual friction coefficients and their temperature differences differ. So it's very important to make the comparison. And some comparison of these two models are discussed in these papers, but this detailed comparison is just beyond the scope of my today's talks. So let me skip here. So I'm talking about the next topics. What makes normal fluid turbulence in T2 state? So normal fluid is viscous and capable of becoming turbulent by itself. How does superfluid turbulence affect it? For example, vortex reconnections injects energy into the normal fluid at scales smaller than the intervortex distance. Can this make the normal fluid turbulent? Or recent nice paper by Luca Garanti's groups found the wakes appear larger than the intervortex distance. So my question is whether such kind of structures are enough to make the superfluid normal fluid turbulent or not. So question is, what makes the normal fluid turbulent in T2 state? In bulk flows, the recent several nice papers suggested the energy injection from superfluid can trigger turbulence of normal fluid. But the situation is, of course, in a realistic channel flows. The normal fluid can become turbulent due to wall shear stress caused by its own viscosity, even in the absence of a superfluid component. Then what is the role of the superfluid turbulence or vortex tangle? What does the vortex tangle do in T2 state? And the vortex tangle should inject energy into the small scales by reconnection or wakes and induce the large-scale deformation of the normal fluid observed by the Tarhasi groups. So such kind of multi-scale interaction accelerate the transition to turbulence or not? I think this is a very basic questions. So this is a basic question about the dual turbulence. And we don't have the definite answer for this problem. So in the last part, I will discuss this problem from just different point of view. So I will discuss how is the superfluid turbulence enhanced by the normal fluid turbulence. We created turbulence in the normal fluid for counterflow, synthetic flow, and we confirmed the resulting amplifications of the superfluid turbulence. And the results are consistent with the experiments by the thoracic groups. What's that? So we carried out the two-way coupling simulations, and we used the traditional approach of the mutual friction. And the normal fluid driven by an ABC type forcing like this. And this method is usually used in a context of the classical fluid dynamics in order to mimic the wall shear stress. And the parameter is 1.9 Kelvin, and periodic boundary conditions are applied in all three directions, so no walls in our simulation. But by using this method, we suppose that we can simulate a wall shear stress. And this is a typical movie of the cases. So there are the snapshots for the taking from the movies. The left figure shows the relatively low amplitude F0 cases. The right figure shows the higher amplitude cases. So F0 refers to the amplitude of the ABC forcing. So we obtained the statistical steady state of vortex tangle. And certainly as the time goes by, the vortex tangle is found to becomes a statistical steady state. And please note, our formulation has two parameters, Vn and F0. Vn refers to the average normal fluid velocity, and F0 refers to the strength of the ABC forcing. So this is the dual turbulence of the two fluids. And the upper figure shows the vortex tangle. Lower figure shows the normal fluid vortices. And if the relatively high value of the forcing, the external forces amplify the normal fluid turbulence, and where the vortex tangle is tended to be localized in the strong normal fluid turbulence regions. So our interest, how does the normal fluid turbulence amplify superfluid turbulence? So in order to characterize the normal fluid turbulence, we introduced two quantities. One is the Reynolds number for the normal fluid fluctuation. So this is our definition for the case. Delta Vn is a fluctuation of the normal fluid. J is some integral length. And nu n is, of course, kinetic viscosity of the normal fluid. And this is our numerical result. So this Reynolds number is increased with the amplitude of the F0. And the lower figure shows the fluctuation, and the fluctuation of the normal fluid velocity. This is a fluctuation amplitude of the normal fluid velocity. And this is our numerical result. The fluctuation amplitude is increased with F0. And for references, Weigo's group reported I should be about approximately 0.35 at 1.85 kelvins. So how does the normal fluid turbulence enhance the VLD of superfluid turbulence? We are coming back to the violence equations. Original violence equation supposed a uniform, homogeneous system. And but we consider the fluctuation of the velocity, the fluctuation of the vortex VLD, vortex length density. And this term shows the correlation between the velocity and the VLD. So by using the Taylor expansion and taking the spatial averages, we obtained something like that. If we consider the stationary condition dLdt equals 0 gives like this. And the point is that this term refers to the enhancement due to the normal fluid turbulence. In other words, this term represents the amplification, the VLD, due to the normal fluid turbulence. Then, as I told before, we have two parameters, fluctuation I and VMS. So the upper figure shows the square root of L as a versus the velocity fluctuation I. Certainly, normal fluid turbulence enhance the vortex tangle, and we found the square root of L should be linear to proportional to the I. And the lower figure confirms the violence relations, and the square root of L as a function of VNS. And this slope corresponds to the gamma, and the gamma depends on the strength of the interaction, and sorry, fluctuations. So this is the last part of my results. So we consider the response coefficient gamma as a normal fluid velocity fluctuation. And we confirmed these coefficients, and we plot gamma as a function of I. So the horizontal axis refers to I, and certainly the numerical results supported, these blue dotted lines is our numerical results. Roughly speaking, this shows such kind of linear relations. And for the references, please remember the Tarasek group status. The Tarasek groups observed I should be 0.35 and gamma is about 190 at 1.85 Kelvin. So what I want to say is this is the Tarasek group state. 1.85 Kelvins, gamma is about just smaller than 200. And but our numerical simulation result is very close to this experimental data. So what I will say, our turbulence in normal fluid is artificially driven, but certainly we achieve the state very analogous to the realistic T2 state. And in this state, we confirmed the vortex line density is significantly amplified by the normal fluid turbulence. So this is that's end. So I'd like to summarize. So I discussed the brief research history and the new perspectives. And finally, I discussed how superfluid turbulence enhanced by the normal fluid turbulence in counterflow. Okay, thank you very much for your attention.
Yeah, thank you, Makoto. Any questions? Logic?
Okay.
Yeah.
Hello, Makoto. This is Larik
Hi.
speaking.
Yes.
Thank you very much for your interesting talk. And one question I have is that, we performed experiments with pure superflow and thermal counterflow. And some questions you asked and addressed in your talk, they might be understood as a difference between thermal counterflow and pure superflow. Just because in thermal counterflow in a channel, the normal fluid can become turbulent simply, as you said, because of kind of classical reasons, while in pure superflow it cannot. So is it possible to simulate the difference between thermal counterflow and pure superflow simply by relaxing the no-slip boundary conditions in a channel for normal fluid. So if you change the boundary conditions for the normal fluid in a channel, then you should see the difference.
Yes, probably. But probably in our simulations, we just solve the bulk situations. We don't take account of the boundary condition due to the walls.
Yeah, I know, but I mean, that was just a suggestion that it could be
Yes,
possibly done.
Thank you very much.
Okay, thank you.
Yeah, it's certainly it's very important. In the next step, of course, we'd like to solve the such kind of simulations by taking account of the boundary condition. But I've retired, but I
Yeah,
don't want to do what. But of course, I know it's a very important suggestion. Thank you, Radik.
Any more questions? So, yeah, I have a question about, so you mentioned the two different approaches to mutual friction.
Yes.
And so you said that they don't quite match. So can you maybe elaborate so how different they are and what are the consequences of that?
Yes, thank you very much for important questions. And yeah, both approach, the two approaches has merits and demerits. And probably in order to investigate the fine structure and probably self-consistent approach would be better. But in order to investigate the very fine scale structure, we need a very fine mesh. And if we consider the large scale structure, for example, the statistical quantities of projectile length, density, something like that, probably traditional approach would work well. And but another thing is temperature difference is just different between two approaches. So I don't know what happens, what causes this approach, this difference. But certainly, we have to necessary to investigate what causes the differences.
Yeah, well, that's very interesting. Why they're different. Then so, well, alpha prime can be negative, right?
Yes, that's right.
Yes. Yeah, but then so is in this self-consistent formulation can also be negative, or is it, how does it
sorry,
work?
I don't remember. Sorry. You're talking about this one, right?
Yes. Yeah.
Yes. Yeah, I just don't remember what happens to the self-consistent approach.
Okay. So any other questions?
I have one actually.
Yes, please.
Yeah, so regarding the difference between the state 2 and 3, could you please comment a bit? Maybe I missed that part, Professor Tsubota.
Yes, you're talking about T2 and T3, right?
Yeah, that's right.
Yes. Just a moment. You're talking about this part, right?
Yeah,
Right.
exactly.
Yes. The difference depends on the shape of the difference of the cross section, the shape of the cross section. So relatively small aspect ratio channel. If the channel cross section is circular or square, in this case, a small aspect ratio channels, the experimentalists observed T1 and T2 transition. But in the large aspect ratio channel, something like that. In this case, for example, aspect ratio is, for example, 1 to 10, something like that. In this case, the only one turbulent state, T3, was observed. So this is still a mystery.
Okay.
So depending, okay, yeah,
But in
okay.
both cases, the normal fluid and also the condensed fluid, actually, they can be turbulent, right?
Yes, we hope so. We hope so.
Okay.
But probably no definite experimental evidence.
All right. Thank you.
We think so.
Thank you. Any more questions? Okay, well, I don't see any more questions, so thank you very much, Makoto. Very interesting talk. And so we don't have a confirmed speaker for in 2 weeks' time, but we have 2 more confirmed speakers. So stay tuned, and hoping we'll be sending invitations to further webinars. Thanks for joining us today, and have a nice rest of the day.